This is an example with a boost converter. I've already connected the circuit with these values. Notice I've connected the gate drive across the gate and source of the MOSFET, which in this case happens to be the ground of the circuit. I'll choose the MOSFET that I had chosen previously. Now for the diode, suppose I want to simulate a diode that is not present in the LTspice library. In many cases, it will happen that a particular device that you have chosen is not available in the default library. In that case, we can try to find the spice model of the device from the manufacturer and import it in our schematic. Suppose I want the model for this particular diode. I'll go to the manufacturer's website. I'll look for the simulation models and I'll download the LTspice model. It's not always so simple for many cases, but you can mostly find the model. If I open this model apart from the comments, I can see the actual model begins with a dot model statement. Dot model files describe the intrinsic spice devices like resistors, capacitors, or in this case diodes. In order to use this model, I'll first copy the first statement of the dot model statement. This is the name of the diode. I will hold the control key and right click on the diode. I'll change the value to the one I had copied. Now I have to provide the model description. There are a number of ways to do this. One way is to copy the whole model description and place it on the schematic as a spice directive. I can place it anywhere. So this is the most portable way to do it. If you share the schematic, the model is also shared with it. If I run the simulation now, I can see first of all there are no errors and I can check the output voltage is around 48 volts, which was expected. Another way to provide the model is to keep the library file in the same folder as the schematic, which I've already done here. So this is the schematic ASC file. I've kept the library file in the same folder. Now I'll copy the name of the file and then I'll use a dot include statement. So I'll type dot inc and the name of the file. So the name of the file should contain the full extension. You can change the extension to anything, but you need to type the extension in the include statement. I can delete the previous model, and if I run it again, there should be no errors, and the result is the same. Suppose I want to change the model as well now. So suppose I want this particular MOSFET. Again, I'll go to the manufacturer's website and I'll download the LTspice model. I'll save it as a text file so I can open it. Now this time the model begins with a dot subcircuit file. So dot subcircuit files define devices that are made up of a collection of intrinsic spice models. So if you see, there are some models inside the dot subcircuit file. Again, I'll copy the first statement after the dot subcircuit statement. And this time I'll hold the control key, right click on the MOSFET, and first I'll change the prefix to X. Then I'll paste what I had copied in the value. Then I can use the model as I had done before. I'll use the second method. I'll copy the file name and use a dot include statement. So if I run it again, I see there are no errors and the voltage is as expected. Now I want to include a resistance in the inductor. I'll right click on the inductance and I'll add a 100 milliohm series resistance. In the previous example, we saw how to check the average input and output power, and we can find the efficiency in that way. Another way to find the efficiency is to use dot measure statements. So I'll start a spice directive and I'll type dot mes, so measure p in. So this is the name of the variable that I want. I want to save it as p in. Avg, that is average, I want to save the average. V in, so I have already named the input node as in. So I'll write V in is the voltage of the in, and the current that goes through the V1 voltage source. Now I'll add a minus sign because this product is going to be negative. Now I'll do the same for the output. And finally, I'll calculate the efficiency. Name it as EFF. Since P in and P out are not circuit quantities, but they are parameters that I have defined, so I have to use the parameter here. So I'll place it anywhere. And before I run this schematic, I'll go to simulate, go to edit simulation command. Since I only want the steady state value, so I'll start saving the data from 15 microseconds. So I'll only get the last 5 microseconds, which is the steady state duration. Now I run the simulation. See, I only got the last 5 milliseconds. The results of the measurement are saved in the spice log file, which I can find under view spice error log. I can also use Control L to open it. Here I see that I can see the input power, the output power, and the efficiency. So the efficiency is around 94%. Now suppose instead of a constant duty, I want to vary the duty over some range. So I'll edit this dot parameter statement and I'll change it to a dot step statement. So I want to vary the duty from zero point 0.3 to 0.7 in steps of 0.1. If I run this simulation again, so I can see it runs multiple times. When the simulation is complete, I can go to the log file again, and I see now there are 5 values, and I can see that the efficiency decreases as the duty increases. If I right click, I can plot this information. The x-axis is the duty, and I can add a trace here for the efficiency. So I can see how the efficiency decreases as the duty increases. I did not increase the duty too high because when the voltages and currents will then become too high for these devices that I had added to handle. You can also try to keep the inductor resistance as a variable parameter and see the effect of efficiency or even the converter gain using dot measure and step statements. Finally, you can use help here to find out the syntax of different spice directives and other help topics as well. You can also find YouTube tutorials and other explanations online. As I said, there's a large online community for LTspice. That's it for this introduction. Thank you for watching and all the best for your simulations.